So if you recall, ions are atoms that have either gained or lost electrons, so they are no longer electrically neutral. So atoms which have gained electrons are typically negatively or always negatively charged because they have more negative electrons than do protons. These are what we call anions. And then our next one is that they're going to have negative oxidation numbers, and they're going to be determined by the number of electrons gained. If it gains 1 electron, it would have an oxidation number of -1 in a compound. If it gains 2 electrons in a compound, then it'll have an oxidation number of -2. Atoms which have lost electrons now have more protons than do electrons, more positives than do negatives, and are called cations. They have a positive oxidation numbers determined by the number of electrons lost. If they lose 1 electron, they have an oxidation number of +1. If they lose 2 electrons in a compound, in a chemical reaction, that they would have an oxidation number of +2. Now, ionic bonding occurs when a cation and an anion, when a positively charged ion and a negatively charged ion are attracted to one another due to their opposite charge. So if we were to imagine, let's say, 2 ions here. Let's say I have a sodium ion, and I'm going to put a little bracket around it just to make it a little easier to say up here. Now, sodium has an oxidation number of +1, and so if you remember why, it's because, you know, sodium has 1 valence electron. We draw the Lewis structure out there, and we said that in bonding, atoms want to gain, lose, or share electrons in order to have that full octet, to basically have the outer electron configuration similar to a noble gas. For sodium, that's going to be losing its 1 electron, which gives it a plus charge right in there. So that's the reason why sodium is going to be a positive ion. I just erased the whole positive that's up here. All right, then let's take a look at, say, if we have chlorine. Chlorine, on the other hand, has 7 valence electrons. To get to a full octet, it's going to need to gain 1 more, and it's going to have a negative charge that's on it. Now, at this point, we have a positive sodium cation, a negative chlorine anion. And what do positives and negatives do? Positives and negatives tend to attract towards each other. And so this positive ion is going to be attracted towards the chlorine because it's negative. The chlorine is going to be attracted towards the sodium cation because it's positive, and they'll stick together. Now, how does this happen? We said the sodium has to lose its electron, the chlorine has to gain an electron, and fortunately they tend to help each other out on that. So typically, cations and anions form in ionic bonds due to the complete transfer of electrons from a less electronegative element to a more electronegative element. So let's go back for a second, take a look at the sodium and the chlorine again, but let's draw it out in terms of what this is going to look like with our Lewis symbols here. So we have our sodium, which has 1 electron. Right here we have our chlorine, which has a total of 7 valence electrons, like this. And so when we start out, this is sort of our situation here, is that what's going to happen is we have simply a sodium atom that's floating around here, a chlorine atom that's floating around here. The chlorine, if you look at where it is on the periodic table, they're both in the 3rd period. Chlorine is much farther to the right, which means it has a higher number of unshielded protons, so it has a higher effective nuclear charge. It'll attract in those outside electrons much more strongly than sodium does. Sodium has a very low ionization energy because it only has 1 unshielded proton, an effective nuclear charge of 1. And so that means that sodium will give up its electron very easily. It's going to want to go to the chlorine because the chlorine is the more electronegative element. So we'll have a transfer of electrons from the less electronegative element, that in the case of the sodium, to the more electronegative element, which in this case is the chlorine. So what will happen is this electron right here will straight out jump over to the chlorine. And so when it jumps over to the chlorine is now the sodium has this valence electron is gone. It has left entirely as it has done its jump over to the chlorine. And so when it does that, now we basically say, hey, this sodium atom now has a positive charge, just like we saw before. This chlorine atom is now a chlorine ion, has a negative charge. And what happens if we have a positive and a negative? That positive and negative tend to attract towards one another, and they'll stick together right there. And so that is basically what happens whenever an ionic bond forms. Now, the number of electrons that transfer, in this case it was 1, is determined by the octet rule. And so because of the fact that that sodium wanted to lose 1 electron to have that full octet, it would lose 1. The chlorine needed to gain 1 to do that here. It doesn't have to be 1. If this were sodium and oxygen, then the sodium would give away 1 electron, the oxygen would have to take 2 electrons. So we'd have to have twice as many sodium ions as oxygen ions, because if each sodium gives 1 and each oxygen takes 2, I have to have 2 sodium ions each giving 1 to give away 2 for the oxygen to take. And so we sort of saw some of that chemical nomenclature once again whenever we were trying to build those oxidation numbers. So next thing we have here is just terminology. A cation which loses electrons, or an atom which loses electrons to become a cation, the term that we use is we say that that atom has been oxidized. And so you talk about metals oxidizing. You said, oh, that that brass is oxidized. The reason why is it's a metal. Metals don't hold electrons very tightly. They tend to be less electronegative, and since they're less electronegative, then they lose their electrons, and so they lose their electrons, and they are said to be oxidized. An anion, or an atom which becomes an anion by gaining electrons, we say is reduced. And say, so oxidation is the process by which cations lose their electrons. Reduction is the process by which anions gain electrons. So ionic bonding between two atoms can only occur if the electronegativity difference between the two atoms is large. So we would not see ionic bonding by, let's say, a carbon and another carbon. Okay? Is that even though we know that sometimes carbon wants to lose all 4 of its electrons, or sometimes carbon wants to gain all 4 of its electrons, carbon's the same element. It has exactly the same electronegativity. There's no reason why the electrons would prefer one or the other. One atom does not pull more strongly towards the electrons than the other one here because their electronegativities are the same. But if we do have 2 atoms that have very, very different electronegativities, they will jump from the atom that has the lower electronegativity, the one that has the higher electronegativity. And this is because that for electrons to transfer completely from one atom to another, there has to be a substantial difference in how attractive the 2 atoms are to electrons. One has to be very unattractive to electrons, low electronegativity, typically a low ionization energy, and one has to have a high electronegativity. And so if the 2 atoms attract electrons about the same, though, not a big difference in electronegativities, the electrons will typically be shared between the atoms rather than transferred. And so they'll be shared, which is a covalent bond, versus ionic bonds, which are a complete transfer. Those electrons have jumped from one atom completely to a different atom. They are no longer associated with that first atom anymore. But in a covalent bond, they just share. They are associated with both of the atoms at the same time. So here's how we know. We said, okay, well, they have to have a large enough difference in electronegativity. Well, how large? We use this. Bonds are considered to be ionic if the electronegativity difference is greater than 2.0. Okay? This number is can vary a little bit. Sometimes you'll see some textbooks that will say 1.7 for this. 2.0 is a good spot to sort of look at this in general here because it really sort of divides the very clearly ionic ones from the ones that are only they're covalent, polar covalent, we'll learn later on. So let's take a look. Let's say we wanted to figure out, hey, what about, let's say, iron and nitrogen? Would they form an ionic bond? All we have to do is look at the electronegativity. And so this table down here, this periodic table, is showing the electronegativity using the Pauling scale. And so nitrogen is 3.04 for its electronegativity. Iron is 1.83. We take a look at, we subtracted those, you're going to get about 1.2. Since that's not greater than 2.0, is that iron and nitrogen would not form an ionic bond. They would form a covalent bond. So that's not going to be ionic bond. What if I, instead of having those two, what if I instead had, let's say, calcium and fluorine? Let's check those two. So calcium and fluorine. Fluorine has an electronegativity of 3.98. Calcium has an electronegativity of 1. Take the difference, 3.98 minus 1 is 2.98. 2.98 is bigger than 2.0, and since it's bigger than 2.0, then we know this will be an ionic bond between these two. All right, so you can sort of get an idea. So calcium and nitrogen, also ionic because 1 to 3.04, just barely is bigger than 2, and so that would be ionic bond here. One thing you also may notice here, you notice that our largest electronegativities are going to tend to be up and to the right. Our smallest electronegativities are down and to the left down here. And so the greater the difference in electronegativity, the more likely they are to be ionic bonds, and 2, the more ionic in character the bond will be. We'll see later on that ionic substances tend to have certain characteristics that covalent substances don't, and the more ionic the bond is, the greater the difference in electronegativity, then the greater ionic character that ionic substance, that ionic compound will have. So this is sort of a way to tell if you have an ionic bond or not. Just look at the electronegativities and that'll let you know that. So let's take a look. Sodium chloride. So will this be an ionic bond or a covalent bond? So let's look at the naming. So sodium is Na right there. Chlorine, we look at the ending, is IDE, which means it's a single element, and so that's just going to be Cl. Hey, we've seen this one before. And so is this going to be ionic? We claimed it was going to be ionic before because we said that chlorine was going to simply straight off steal away the electron from sodium. So sodium has a +1 oxidation number, chlorine is -1, so the formula should just be NaCl, right? And so that should be our formula right there using our nomenclature rules. But is it going to be ionic or not? So let's take a look. We go to the periodic table, we look at sodium. Sodium right over here has an electronegativity of 0.93. Chlorine has an electronegativity of 3.16. So all we have to do is simply say 3.16 minus 0.93. And so whenever we do that, we should get, what is that, 2.23. So 2.23 is going to be greater than 2. And so because it's greater than 2, then we said this is going to be an ionic bond. And so sodium chloride is ionically bonded. So this is just table salt. And so we know that's going to be an ionic bond. Let's try our next one here, calcium oxide. So calcium oxide. The calcium is Ca. Oxide, once again, ends in IDE, so it's going to be a single element, which would be oxygen. Balancing the valences out. We can figure out what calcium is because let's just try this the old-fashioned, or the new-fashioned way, if you will, using our octet rule, so we don't look it on the periodic table. Calcium has a total of 2 valence electrons. Oxygen has a total of 6. 1, 2, 3, 4, 5, 6, like this. And so because of that, we'd say, well, how are they going to get to their full sets? Calcium, we would expect, wants to get to a full set by losing its 2, because calcium is, looking at the periodic table, is off to the left, a pretty low electronegativity, not a very high ionization energy, and so it's going to lose its 2 electrons right there, and so calcium, as a result, is going to have a +2 oxidation state. Oxygen, on the other hand, wants to gain 2 electrons, and so since it wants to gain 2 electrons, it's going to have a -2 oxidation state, and so we should just have CaO because they already balance out. Now, are they ionic or not? So once again, we look at their electronegativities. Calcium has an electronegativity of 1.0. Oxygen has an electronegativity of 3.44. 3.44 minus 1.0 is 2.44. Since 2.44 is greater than 2.0, then we say yes, this is going to be an ionic bond. So calcium oxide is ionically bonded, not covalent. Aluminum nitride. So aluminum nitride, aluminum is Al, nitride is just going to be nitrogen. So drawing this out, we can figure out how many electrons. Aluminum has 3 valence electrons, so that means that it's going to either have to lose 3 or gain 5 to get a full octet. And so losing 3 is going to be more likely, especially if you look at where aluminum is on the periodic table. It's a little farther left than most of the things in its period, only has an effective ionic charge of 3. So it's going to lose those 3, which means aluminum would be +3 for its oxidation number. Nitrogen, on the other hand, look at the periodic table, has an atomic number of 5. So it has 1, 2, 3, 4, 5 valence electrons. And so of those 5 valence electrons that it has, is it wants a full octet. So to do that, it's going to have to gain 1, 2, 3 electrons, and if it gains 3 electrons, it would be -3, which is that thing that nitrogen usually is as a nitride. So in order to figure out whether this is ionic or covalent, because it's possible that they may share electrons, it's possible that the nitrogen might steal them from the aluminum. If it's ionic, it will steal them. If they share them, it's covalent. So we look at the periodic table again. Nitrogen is an ionization energy, electronegativity of 3.04. Aluminum is 1.61. So we say 3.04 minus 1.61, and we say, ooh, that is only going to be about 1.43. 1.43 is going to be less than 2.0. So that means that aluminum nitride is not ionic. It is going to be covalent, so it's not ionic, unlike these first ones that we saw here. So that's how you'd show that one is not ionic. last one we look at is magnesium fluoride. So for magnesium fluoride, we have MgF. Okay, so let's look at try to figure out our oxidation numbers. So Mg is magnesium, 2 valence electrons right here. And so it wants to get that full octet. It's easiest to do by losing the 2 electrons it has to go back to the previous noble gas state. And so then magnesium is going to have an oxidation number of +2. Fluorine, on the other hand, drawing it out, has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. It's to get to a full octet, it's going to want to gain 1 electron, and so therefore it's going to be -1. So to make these balance out, all the previous ones we had here just happen to turn out nicely where we didn't have to balance them here. But for this to work, we got to have 2 fluorines, and so this means we're going to have MgF2 is going to be our formula for this to get these the oxidation numbers to balance out. But is it ionic or is it covalent? So we turn to the periodic table again. We look at magnesium. 1.31 is our oxidation, or is our electronegativity for magnesium. Fluorine is 3.98, so we say 3.98 minus 1.31, and so pretty clearly that's going to be above 2. That's going to be 2.67, I believe. And so since that's larger than 2, this is going to be ionic bonding right here. Oh, sodium carbonate. Actually, there's one last one we're going to look at here. This is a little bit of a special case because you start this off, you say, oh, sodium's in A, carbonate is, ends in 8. This is not just a single element. So we have to go and look at our polyatomic ion sheet because 8 is a polyatomic ion, and carbonate is CO3. All right? So it's CO3, but that's that polyatomic ion. It doesn't have an electronegativity here. Well, here's the trick on this right here. If you have a polyatomic ion in a compound, it's automatically ionic. Because here's what a polyatomic ion is. A polyatomic ion, in this case, this CO3, which has, I'm going to draw a little ion symbol around it, which is a 2-, right? It's got a -2 oxidation number right here. The C and the 3 O's are covalently bonded with one another. But when they covalently bond, they end up with an overall negative charge, and so they form a negative ion. They are, as we said, polyatomic ions, and if they're ions, then they have an overall charge. So that's CO3, -2, the carbonate's -2, the sodium is +1, as we've sort of seen before. This is automatically going to be ionic, because what's going to happen is that CO3 is going to go with that sodium ion, and since the sodium ion is positive, the CO3, the carbonate ion is negative, they attract to one another, and so the negative carbonate ion, the positive sodium ion want to attract to each other. And so if you see a polyatomic ion, it's automatically going to be an ionic bonding. Even though there's covalent that goes on within the polyatomic ion, there's ionic between the polyatomic ion and the other ion that's involved, either the cation or the anion. So that's sort of how you deal with a polyatomic ion. So structure. Ionic substances do not form molecules. Covalent substances do. So water, you have water molecules, that's not ionic. We know it's not ionic because ionic substances never form molecules. Instead, they form what's called a crystal lattice. They're basically repeating anions and cations. If you look at this picture over on the right, you can sort of see that. You can see our green anions. They have the negative signs in them showing that they're anions. We have the dark grayish or whatever those are, cations. They're a little smaller. And so you can see that what happens is we have this repeating structure of cation, then anion, then cation, then anion, then cation, then anion, and so on and so forth. And that's not just left to right. That's also up and down. You can see it goes cation, then anion, then cation, cation, then anion, then cation, then anion, then cation, then anion, and so on and so forth. And it also goes sort of backwards three-dimensionally. We have cation, then anion, then cation, then anion, then cation, then anion, then cation. And so it's just this repeating process of anion after cation after anion after cation, arranged so that the cations and anions alternate. And so basically what's going to happen here is that this cation right here is going to pull in that anion and that anion and this anion and that anion and the ones that are in front and in back of it, they stick them all together. And at the same time is that this anion right here, I'll try to change color so we can see it a little better, this anion right here is going to pull in that cation and that cation and that cation and that cation and the ones in front and in back, and it's going to stick all them together. And so we have this sort of large, blob's not the right word because this is very, very well structured. It's very, very well ordered. In fact, it is a crystal. That's what a crystal basically is. Lattice just refers to the fact of the regular repeating characteristic of these anion cations that go on here. And this can go on indefinitely. When you have like a single crystal of salt, it's nothing but a giant chunk of these repeating sodium cations and chlorine anions that you have here. If it's sodium chloride as its salt right here, because it's plus and minus right there, as they ionically bond. And so this is what you get with ionic bonds. So when we talk about ionic substances, like for example K2O, we don't mean there is a separate group of 2 potassium and 1 oxygen atom. It doesn't mean that there is, there's an oxygen here and then there's a potassium right here and a potassium right here, like we sort of like this. They sort of stick together and they act like one chunk like this. That's not how ionic bonds work. Instead, what they're going to do is they're going to form sort of this nice repeating pattern where you're going to have whoops, that's not the symbol I wanted, where you're going to have basically these repeating systems where you'll have something like a potassium, an oxygen, then a potassium, and then an oxygen like here. And so I'm sort of getting out of the way. Let me try this a little smaller so I can see this a little better. So like a potassium, oxygen, then a potassium, oxygen, and then a potassium, oxygen. And it would so on and go like that. And you might have an oxygen with a potassium and an oxygen with let's see, how would I work this here? Potassium and a potassium like this. Now if you notice when you look at this, the ratio is still a 2-to-1 ratio. Is that in our picture we have here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 potassiums and 1, 2, 3, 4, 5 oxygens. And so while they still have this repeating over and over again pattern like this, they're in a 2-to-1 ratio, which is the reason why it's K2O, but they don't sit out as just one chunk, one molecule of a K combined with an O like this here. It's a crystal of repeating K plus cations and O2 minus anions with a 2-to-1 ratio of the ions repeating in the lattice. And so that's basically how ionic solid substances form, the structure of them. Now, properties. Ionic compounds tend to have a very few distinctive properties. One is they're generally solids, and they tend to have high melting points. 2, they tend to dissolve in polar solvents, and we'll talk about what that is in a second, but they don't dissolve in nonpolar solvents. So polar solvent would be something like, for example, water. A nonpolar would be something like hexane, like one of the parts in gasoline, things like that. Ionic substances, ionic compounds, if you do melt them, and it takes, as we said, they have high melting points, so it takes a lot of energy to melt them. They'd be very, very hot. But if you do melt them, or if you dissolve them into a liquid, into a polar substance, as we said, they tend to conduct electricity very, very well. Okay, these are called electrolytes. You know, you talk about like Gatorade, and if you look on the bottom, you look on the back of your Gatorade bottle, you're going to see all sorts of ides that are in here. It'll say things like, you know, potassium chloride, sodium chloride. You'll see these right here. If you look at those substances, figure out what their chemical formulas are, look at their electronegativities, you're going to find that every single one of those, or at least all the ones that end in I that are on the back of that bottle, are all ionic compounds. And so they're ionic compounds, so they dissolve well in water because water is polar. And if they dissolve in water, when they do that, they tend to conduct electricity well, and so they call them electrolytes. Okay, electrolytes, because they conduct electricity right in here, as well as doing things that help to keep you well hydrated. Next thing, ionic compounds tend to be brittle. They tend to shatter rather than bend when a force is applied. I can talk about that one just really quickly here, and the reason why that's true is because of the fact that they have these regular repeating patterns. Is that if you were to put a force on this, that you push really hard on this side and you push the other way on this side, is they will tend to crack along this along some plane that works in between this. They don't tend to bend, because to bend that these atoms have to slide out of place. Like this positive would have to slide into this spot right here, that negative, that anion would slide in between the other anions. It doesn't want to do that. As soon as you put it in that place, it's going to push away, because negatives are not attracted to other negatives. When it pushes away, it's going to force this substance apart. The term is going to cleave, it's going to split, and it's going to shatter. And so they tend to be very brittle, ionic substances are, when the solid form. They shatter rather than bending whenever you apply a force. So let's look at the first one, solids with high melting points. Why do ionic compounds have high melting points? The reason why is because each ion in the crystal lattice is surrounded by ions of the opposite charge. That makes it incredibly stable. Each ion is held in place very, very strongly because, you know, hey, you've got this positive charge, and the positive charge is surrounded by negative charges. The cation is surrounded by anions. They hold it in place. If they hold it in place, it's going to tend to be a solid. Is that they still will jiggle around. There still is some ionic motion as they jiggle around because they do have temperature. There is some heat or some thermal energy that they possess, but they don't really go anywhere very easily. You have to get these things going extremely quickly. You have to heat them up a lot to get that positive to start moving out and get the negatives to start moving away from all the other positives that surround them. And so since it requires a large amount of energy to do this, is that, you know, you have to give them a lot of energy to break away from the strong forces of their neighbor ions. And so this is a result, they have a high melting point. All right? Next one they have here is, we said they dissolve in polar solvents but not nonpolar solvents. So let's look at what these are. So first thing, a solvent is something that dissolves something else. We'll wait to solutions. We'll really cover this pretty heavily here. So like if you have salt water, the solvent is the water in that case. Oftentimes you'll need to have like something on your hands that's sticky, and so like tar or something, you use a solvent to get it off here. If you're cleaning paint brushes, you may use a solvent to remove paints, especially if you have like acrylics and things like that. So solvents dissolve something else. Polar solvents, the word polar deals with the word pole, but a polar solvent is a liquid made of particles that have one positive end and one negative end. And so we have a particle here that has a positive end and a negative end. And so since one end is positive, the other end is negative, we call it polar because it has one pole on one end and one pole on the other. And so polar solvents, water is a good example. These tend to dissolve ionic compounds because the charged ends of the solvent molecules attract the charged ions out of the lattice. And so if we basically have this out here, is that the cation that's in the crystal lattice is going to be attracted to the negative end of the dipole molecule. The anion that's in the crystal lattice will be attracted to the positive end. And so basically these little polar particles in the solvent just sort of slowly one by one pull away the cations and the anions out of the crystal lattice and dissolve it. And so that's what tends to happen. Now nonpolar solvents, on the other hand, they don't attract the ions. So hexane is an example of this. It's a common component of gasoline, as we said. And so if I just have this little zero guy that floats out here, and so here comes my nonpolar substance, no positive or negative end right here, is that what's going to happen is, you know, the positive cation sitting right here, hey, it's surrounded by all these negative anions. It's like, hey, I like where I am here. And there's nothing that's attracting it towards this guy right here. It just doesn't attract it at all. And so as a result, those cations and anions are going to stay in place. So nonpolar solvents do not tend to attract ions and so cannot dissolve the ionic compounds. Polar solvents, on the other hand, because they have charged ends on them, are able to pull those ions out of the crystal lattice. Next thing, when melted or dissolved, ionic compounds tend to conduct electricity well. So the reason why is that if ionic solvents are melted, the ions can move around. Well, so now you have mobile charged particles. So these charged ions can then flow. And so if I have a bunch of charged ions that are starting to move, what is that? That's called electricity. Okay? This will only happen if you sort of give them a reason to move. Like, for example, if we put a negative plate over here and a positive plate over here, then all the negative ions are going to move towards, or the positive ions, or the cations will move towards the negative plate. All our negative ions, or anions, are then going to move the other way towards the positive plate, and I have an electric current. And so melted things tend to, melted ionic substances, because they're made of ions, charged particles, when they start moving, they conduct electricity really well. If the ionic compound, on the other hand, is dissolved, the exact same thing happens. These ions are now floating around in the middle of the solvent, and so they're free floating. They're not attached to the anions now, and so they can flow through the solution, and they conduct electricity well. And so this is what we called, again, these are electrolytes, right? So we said electrolytes are the substances in which we have ionic substances which are dissolved in liquid or dissolved in a solvent. And so because they are free to move around, they do conduct electricity very well.